All right, so technically segment 5, but the chapter for Wiley is broken into two parts. So it depends on how you want to look at it. It could be the first part of, or excuse me, the first segment of part 2, or the fifth segment of chapter 4. Okay. I warned you ahead of time in the first part of the chapter. We got into net ionic equations. I said that'd be a big key. The focus of this section of chapters is going to be predicting the products. So here it comes. Okay. So we'll be looking at metathesis reactions, reactions where anions and cations exchange partners. They're also called double replacement reactions. So if you had Chem 110, that's how you would have learned them. You would have learned them by title of double replacement. So in a double replacement reaction, what we see is here we have lead nitrate. So we have lead 2 nitrate. It's mixing with Ki. And you might remember this reaction. Then we ended up with lead 2 iodide and potassium nitrate. We saw that this was a solid. We called that a precipitate. And so that dropped out of solution. And then we had these ions would actually cancel out with these ions over here, right? And then we would generate our net ionic reaction. Now those are also referred to as precipitation reactions because we have a precipitate. So metathesis reactions are where a precipitate will form. So how can we predict if compounds are going to be insoluble or not? Well, basically you have to know your solubility rules. So if you have the text and you look at table 5.1, they give you some solubility rules. I'll post a slide, either be a slide or maybe a Word file. I know currently it's a PowerPoint slide. Oh, now that I think about it, I might have to recreate it. So it'll probably be a Word document now that I think about that. But basically what we're going to be doing is looking at soluble compounds. And so all salts of the alkali metals in group 1A are going to be soluble. All salts containing ammonium, nitrate, perchlorate, chlorate, and then acetate are soluble. All chlorides, bromides, and iodides, so salts containing any of those, are soluble except, and this is why people usually end up hating chemistry, because we give you a bunch of rules and then there's exceptions. And of course I like to make the joke that we have rules for our exceptions that have rules that are exceptions to rules that don't follow the rules at all. Follow that one. And there's some truth to that. The higher up you go, the more exceptions you find. So if you only have to do one semester, then you only have a few exceptions. You end up with a degree, you'll see there's tons of exceptions. So the exceptions here are for silver, lead, and mercury. Okay, and notice the subscript for the mercury, it's a 2. Okay, all salts containing sulfate are soluble, except those of lead, calcium, strontium, barium, and that mercury again. All right, insoluble compounds. So all metal hydroxides, right? So ionic compounds containing OH, and all metal oxides, ionic compounds containing O2 minus, are insoluble, except those of group 1A and those of calcium, strontium, and barium. When metal oxides do dissolve, they react with water to form hydroxides. The oxide ion then does not exist in water. For example, if we take sodium oxide and we mix it with water, it is soluble, but it breaks down to NaOH. Okay, so it gives us N sodium hydroxide. Now, all salts containing phosphate, carbonate, sulfite, and sulfide are insoluble, except those of group 1A and ammonium. So, which of the following compounds then are expected to be soluble in water? So if we look at calcium acetate, would we expect that to be soluble? Now you want to make sure you have those solubility rules, because if it's soluble, you can look at the solubility rules and see that all acetates are soluble. So we would say yes. Okay. How about iron carbonate? So iron 2 carbonate, FeCO3. Again, you're going to look on the list. We don't see iron anywhere, and that's because we're going to be looking for anions. So you almost always want to look for the anion and then see if the metal is an exception. So here we would be looking for the carbonate, and it says that all carbonates are insoluble except, and in that list iron is not one of them. So that means this would be insoluble. Finally, we have silver chloride. So again, we'll look up that anion, chloride. Chloride is always soluble except, and then here we see silver, and silver is one of the metals, and so silver chloride is not going to be soluble. All right, so the double replacement reaction itself, we give it a formula. We say AB plus CD goes to AD plus CB. The order here doesn't really matter, so we could have had CB plus AD on the product side, and that would have been fine. Remember, this is happening simultaneously, so you're creating both of those products at the same time. The cations and the anions are simply changing partners, right? The ions themselves don't change, so they're changing partners, but they're not changing charge, okay? Formulas of products are then determined by the charges of your reactants. So in other words, for a metathesis reaction, if we have iron 2 in the beginning, so let's say A is Fe, and it's got a 2+ charge. On the product side, it's also going to be a +2 charge. Okay, so iron 2 in the beginning will be iron 2 in the end. Hopefully that makes sense. Okay, so iron 2 in the beginning will be iron 2 in the end. So remember, iron can change charges. Now, iron will be able to change charges in a reaction, but that's going to be a different set of reactions. We'll talk about that later. Okay, so for now, if it's a metathesis reaction, a double replacement, the charges have to remain the same. Now, it can only occur if solid gas, a weak electrolyte, or a non-electrolyte products form. Okay, so we have to be able to form something that's not soluble. If we form a solid, then it forms a precipitate and it drops out. If it forms a gas, then the gas, we say, goes up and it's out of the solution. Or it forms a weak electrolyte, so it's only partially soluble, it's partially insoluble, right? Or it forms a non-electrolyte. So if it forms a molecule, then even though that molecule may not be a gas or may not, so in other words, if we form water, so if we make water, water would be our non-electrolyte molecular compound that doesn't break apart, and so it forms water. So otherwise, all the ions will remain as spectator ions. Okay, so predicting products of double replacement reactions, what you want to do is identify the ions that are involved. Okay, distinguish between subscripts that count ions and those that are characteristic of a polyatomic ion. So don't mix up your polyatomic ions. Your polyatomic ions are not going to break apart in this. Okay, not in a metathesis, not in a double replacement reaction. You're simply swapping the partners around. So if I have nitrate in the reactant side, I'm going to have nitrate in the product side. Assign states using your solubility rules. So look at your individual pieces and say, hey, is this one soluble? Yes. Is that one soluble? Yes. Go to the product side. Is this soluble? Now here, what you might have to do is look at the different combinations. Then balance your equation. That'll be last. It's always last. Balancing is always last after you predict your products. So we're going to take 2HCl plus calcium hydroxide, and we're going to form calcium chloride and water. And there's our molecular liquid, right? So that means we know this reaction is going to happen. Now you can count the subscript here. You know, that subscript there is going to have to show up somewhere. So your ions here are H plus, Cl minus, Ca2 plus, and 2OH minus. Okay, so the calcium, you know, is going to go with the chloride because it showed up with the hydroxide. It's now going to be with the chloride. And the hydrogen is going to go with the hydroxide. So you're literally just switching them around. Now, we'll write molecular equation for the metathesis reaction. So we'll show that production of water. And then we'll determine which ion combinations will form either the insoluble salt, water, which is what we made in that reaction, a weak electrolyte, or a non-electrolyte, or a gas. Okay? From there, we can then translate our molecular equation into our ionic equation. Then we can cancel everything and get our net ionic equation. So all the stuff we saw in the first part of the chapter is coming back now when we do our predictions. And then you can check for a driving force, because if you didn't form one of those things, then this reaction is not going to take place. And then we would say NR, no reaction. So capital N period, capital R period. All right, so what will be the solid product of the reaction? Calcium nitrate plus sodium carbonate. So again, I'll give you a pause. You can work on your own here for a second before you start up again. All right, the answer is going to be CaCO3. Now, hopefully you came up with that, but if you didn't, what you're going to do is you're going to take your calcium, and you're going to see that it's here. And so now it's going to go with the carbonate. So we have calcium carbonate. Now, the other product is going to be sodium, Na, single plus, nitrate, single minus. Now, if I want to balance them, I had 2 here and a 2 there, which means I'm going to need a 2 here. And now what I can do is go to my solubility rules and say, okay, remember we're going to use our anions. Are there any carbonates that are soluble or insoluble? And according to our solubility rules, it says all carbonates are insoluble except. Then we have to say, okay, is calcium one of those exceptions? It's not. That's how we know that's going to be the precipitate. Then we look up nitrate, and it says all nitrates are soluble. No exceptions. So that means sodium nitrate then is soluble. They're just spectator ions. Okay, so hopefully that's making sense how we do that. So predict your products. We have lead 2 nitrate and calcium hydroxide. So if we change the products around, we get PbOH and CaNO3. We know that all metal hydroxides are insoluble except, and lead is not one of the exceptions. How about barium chloride plus sodium carbonate? And here your products will be barium carbonate, because all carbonates are insoluble except, barium's not an exception, and then sodium chloride. All right, how about sodium phosphate and mercury nitrate? So again, you're going to swap those around. You can balance it, and you get 6 NaNO3, then mercury phosphate. And here, the phosphate, all of them are soluble except, and mercury is one of the exceptions, and so it's insoluble. Sodium chloride, calcium nitrate. Okay, we get no reaction, right? So your products are calcium chloride. All chlorides are soluble except, and calcium's not an exception. And then sodium nitrate, and all nitrates are soluble. And so since everything stays in solution, everything's a spectator ion, everything cancels out, and you get no reaction. Now, inevitably, someone always asks when we have a live face-to-face lecture, well, is that really what happens? And the answer is yes. But if I boil all the water off, because I think what they're trying to get to is this, if I wanted to try to get a solid out of this and I boil that water off, what I'm going to get are different combinations of sodium and calcium salts, right? And depending on what it is, I mean, we could devise some methods to separate things out, but it's going to be a random pot of different salts is what we'd end up with. And so hence no reaction. It'd be too much work to try to separate things out. All right, so learning check here, predict the reaction that will occur when aqueous solutions of cadmium nitrate and sodium sulfide are mixed. Write molecular, ionic, and net ionic equations. So your molecular equation then would be cadmium nitrate plus the sodium sulfide. Now we know it's a metathesis reaction, so we're simply going to switch the partners around and then balance it. Then we're going to check our solubility rules, and we're going to see that cadmium sulfide is insoluble. Sodium nitrate is soluble, so it gets an AQ. For our ionic equation, we'll simply break it apart, right? So cadmium will be a +2, we'll have 2 nitrates at -1, right? We'll have 2 sodiums at +1 and a sulfide at -2. The products will be cadmium sulfide. Notice it stays as a solid, so it doesn't break apart into its ions. Then we have the nitrates and the 2 sodiums. We see everything cancel out here. So the nitrates cancel it out, the sodiums cancel out. We then get our net ionic equation, which would be cadmium 2 plus the sulfide gives us cadmium sulfide. All right, so write molecular, ionic, and net ionic equations for the reaction that occurs between lead 2 nitrate and then iron 3 sulfate. Give you a chance to pause. All right, so your molecular equation then would be 3 lead nitrates, 1 iron sulfate. You're going to form 1 lead sulfate and 2 iron 3 nitrates. For your ionic equation, you're going to break these pieces apart. Again, we'll use our solubility rules during the molecular equation here to see that the lead sulfate is insoluble. So when we go to break these apart, we're going to have 3 leads. 3 times 2 gives us the 6 nitrates, 2 irons, 3 sulfates. That looks like a typo here. I think that's supposed to be a 3. Right? They have 6, but there's no 2 out front here. I'm not sure what they did. That should be a 3 there. Let's see. And then on their product side, you got the solid PbSO4. We have 2 irons, and then 2 times 3 gives us 6 nitrates. Now to move to our net ionic equation, we know we're going to cancel out those nitrates. You would have thought they would have caught that here, where the 2 irons disappear. And then when we write, nope, they sure didn't catch it. They ran it all the way through. Wait a minute, so where's this 6 coming from? Because now they're making that 6 cancel out at the end. But 6, I'm not seeing it here. I think we have a craziness going on here, because let's back this up. Nothing like making a mistake when you're doing a video, because I'm not seeing what they're seeing. All right, so we had lead nitrate, we had the iron 3 sulfate. When we made the ionic equation, we did 3 leads, 3 times 1. 3 times 2 gave us the 6 nitrates. There's nothing here, that's a 1. We have 2 irons, 2 irons. It is balanced, right? So we have 6 nitrates over here, 6 nitrates over there, 2 irons, 2 irons, 3 sulfates. Well, they left the 3 out here. This is half the problem. There should be a 3 there. All right, that gives us 3 sulfates and 3 leads. Yeah, I'm not sure why they messed that up there. So then we have 3 leads, 6 nitrates, 2 irons, 3 sulfates, not 6. Then we have 2 irons, 6 nitrates, and that should be 3 PbSO4s from the balancing. All right, then for the net ionic equation, the 6 nitrates go out, the 2 irons go out. And so what we should be left with, and I'm not going to use theirs, I'm going to use ours. We have 3 Pb2 plus aqueous plus 3 SO4s 2 minus produces 3 PbSO4. Now, maybe it's because the grad student wrote must make lowest possible whole number coefficients. Maybe they got confused. But here's where we're going to do that. We have 3, 3, and 3. So the 3's are going to cancel out. It's going to leave us 1 lead, 1 sulfate, 1 lead 2 sulfate. Okay. So hopefully that wasn't overly confusing. Wasn't expecting them to have errors in their slides. I should have been better prepared for that, since I know in the later chapters we would find errors in our live lectures all the time and then make jokes about it and blame grad students, because it's usually grad students that are putting these slides together. All right. So your turn then. Will mixing aqueous solutions of magnesium acetate and cesium chloride yield a precipitate? So the quick and dirty here is look up those anions. All right. So we have acetate. Does acetate form an insoluble salt with magnesium? Obviously not. What about cesium? No, it doesn't. All right, how about the chloride? No, magnesium and cesium, neither one of them are exceptions, and so no, we will not have any precipitate. Okay, so your molecular equation would be magnesium chloride and cesium acetate, which means they all break apart, they're all soluble, which means everything cancels out. All right, will mixing aqueous solutions of K2SO3 and barium nitrate yield a precipitate? Well, here we're going to look up the I said sulfate, but it's sulfite. We're going to look up the sulfites, and we're going to see that what? All sulfites are soluble except barium. All right, and then all nitrates are soluble. So yes, we are going to have a precipitate this time. When we write out the molecular equation, we're going to see that barium sulfite forms a solid. And so therefore we'll get a net ionic equation. All right, well, mixing aqueous solutions of ammonium hydroxide and zinc perchlorate, chlorate yield a precipitate. The answer here is going to be yes, right? All hydroxides form a precipitate except, and zinc is not an exception. Okay, see things cancel out, left with a net ionic reaction. All right, so next we'll look at predicting acid-base reactions. That'll be our next segment. So we're going to stop here. I apologize for the mishap on the last reaction we had looked at there when we broke it down for the lead. I think it was, can't remember what it was, but lead whatever. Hopefully that wasn't too confusing. If it was, let me know. I'll break it down a little bit better in a single video for just that one problem so you can see how it's supposed to turn out. All right, until the next segment.